Okay, so today's video is going to be about quantum mechanics. In quantum mechanics, we'll be talking about uh, entanglement. Okay, in entanglement, so what is entanglement? Let's suppose we have two particles, and we have two particles, particle 1 and particle particle 2. Okay, so let's suppose they're doing something, and particle 1 is doing C1 and C2. Okay, this is what particle 2 1 is doing. Particle 2 on the other hand is doing something else. Particle 2 is doing A1 plus A2. Okay, they are non interacting particles. Interacting particles. Interacting particles. Okay, so what do I mean by non-interacting particles? That they are somewhere off and they have no connection, physical connection between them. But if somehow, okay, somehow, what if we could build a connection? Okay, we could build a connection in a way that they don't have to come closer to each other. Okay, here. They don't have to come closer to each other. No need for no need for physical connection. Okay, that they're not touching each other, no contact between them. Okay, that could be said as let's say how could you say it? Yeah, C1 plus C2 wait, let me just write, then I'll tell you. So this is how we could connect it, and this over here, our friend is our friend tensor. It's called tensor product, showing that it's multiplying and not multiplying in a weird some way. Okay, so we actually looking at them without them having any physical or any connection between them. Okay, so this over here, okay, this over here, if there's some, let's suppose let's suppose if I assign C1 plus C2, okay, C2 to a C something, okay, and this is a1 plus a2, okay, equal something known as, I suppose we say it's, what could we say it is a, this is what this one is. So if we combine them, sorry, I should make it more clear. If we combine them, we should get C something like whatever that, I'm just giving an example, plus the square, absolute square, a to a something equal, it should equal 1. If it equals 1, that means bravo, you have a, this is what you call entanglement. Connection, building a connection between two non-interacting particles in such a way that change in one particle will affect the change in another particle, but keeping the fact in mind that their sum, the probability of the measurement, will equal 1. This one, okay. So what we could say is that, let's suppose we take a scenario or a example, okay, and we say that two people, Alice and Bob, have two particles with certain spins, okay. They have two particles, sorry, they have two particles, and these two particles, let's suppose one is spin up, this will denote the spin up. Let's set it up first, spin up, and this is spin down, right? Okay, so let's suppose we put them in a mixed state, in two states. How? Doesn't look like I'm making logic gates. All of those arrows. Okay, so here, let's suppose we have mixed state. In the state, let's suppose we have these two spins. First state is this. One, two, one, with tensor product in middle. So here, what we will be looking at is these two things, okay, these two states. So let's suppose Bob makes a measurement, okay, he makes a measurement, so what we will do, what will happen is that if he measures, let's suppose he measures over here, spin down, okay, in the first one, this one, okay. So what will happen is that now there's something known as wave function, okay. Wave function will collapse, collapse. Okay. Now, what will be the consequence of wave function collapsing? Before you didn't measure, there was the wave function was there. Okay, this is wave function. Now, when we were not measuring, the wave function existed. Okay, the wave. Let's suppose what do we call the wave function is that when we don't measure anything, that time the particle, the two particles, because these are two different particles, right? This is particle 1 and particle 2, particle 1, particle 2. So what this statement over here, this statement over here is showing that I think I should have explained what it means before writing it. Okay, so let me see. Duplicate. All right, cut. So let me show what it means. So in visualization, this over here is particle 1. This over here, my friend, is particle 2. Okay. So what we are actually observing is that these two have spins. Okay, these have spins, but they spins in such a way that before measuring it's in superposition. Okay, what do we see is that, what I mean by this is this is what I mean. If I draw, this is our particle. The particles are here. So I just made them big so I could show the difference. At the point when they are in superposition, okay, what you will see is that they over here, they will have both spin up and spin down for both particles. Wait, let me change color. They both will have same spins at the same time. Same spin mean both up and down, both of them. Okay, but this is what the condition is before measurement. So that's what's happening here. So when Bob made a measurement, these two particles, like, the wave function broke. Now the wave function either took this state or this state. Okay, so that means, suppose if Alice is here and Bob is here. Okay, so if Alice, so let's come down here. Alice made a measurement. Now suppose because I have Alice on this side, so I'll make Alice made a measurement. Now, or we could just replace, not to confuse, Bob, Alice. Okay, so let's put them far away from each other. The distance between them is light years. Okay, light years. Now, the moment Bob made a measurement, the wave function broke. Now we have only one state, and it's this one. Okay, now what Bob will measure is that he will see that his particle over here is in horizontal or a vertical state. Not horizontal, vertical state. He is in a up direction, and for Alice it will be a down direction. So When it broke, the particle became, for a Bob it was up, Bob's particle turned into up state, or a spin up, and Alice's spin down. That's, my friends, is entanglement. Even though there was no connection between them, the change in the let me fix my words, the measurement in one particle affected the other particle no matter its distance in a such way that their properties are linked. I think that's the best definition I have given for entanglement. So